And if we have this, maybe we can get to the point where we can actually prove properties about a system that don't rely on probabilistic arguments. Right? Any security technique that depends on keeping a secret relies on a probabilistic argument about how hard it is to guess that secret. If we can find some way that doesn't rely on a secret, then maybe we can make a solid argument that it's always secure. So here's an idea for how to do that. So we want a secretless structure that provides security using diversity techniques. And the idea is that if we have some way of sending the same input to two variants, so we have an input replicator that takes input, sends that same exact input to two variants on our server, and then we have a monitor that looks at what the variants do, and if they do the same thing, sends the output back to the client. If they do something different, and in particular if we can construct variants so any attack that succeeds on one of the variants is guaranteed to make the other one crash, then the monitor knows something's wrong, recovers the system in some way, and doesn't send output to the attacker. So what do we need to make this work? We need some way of making variants that are disjoint. We need to know that anything that works on variant A is guaranteed to make variant B crash, and anything that works on variant B is guaranteed to make variant A crash. So we could think of various things we could use for this. We could use memory addresses. We could say that all addresses that start with a 0 bit are valid in A and invalid in B, and all addresses that start with a 1 bit are valid in B and invalid in A. And as long as the attack required absolute addressing of memory, we would have a disjoint set of variants there. Now, if the attack could use relative addressing, this would not work. So one example is instruction sets. So the goal is to make the variants disjoint, and we can take all possible instructions. And so here's a set of the instructions in x86, and we could take all the possible instructions and say we're going to take half of the instructions and make them valid on variant A. And we're going to take the other half and make those valid on variant B. Now we need the second property, which says anything that's valid on variant A is going to cause variant B to crash, and vice versa. So we're going to take the other instructions and make the way we execute these two variants so that all of those instructions cause them to crash. And if we can achieve this property, then we know that any attack code can't work the same code on both machines. It's not a problem for the server code because we can compile the server in different ways. We can compile it for variant A to use the blue instructions, and we can compile it for variant B to use the green instructions. Well, actually, the cyan instructions that are valid on variant B. Right, so we compile it, produce two different executables, but we know that there's no one fragment of code that could run successfully on both variants. Okay, so actually implementing this poses lots of challenges. We haven't implemented this yet. We're working on this now. There's the engineering questions of how do you actually implement this design. Right? We need to build an input replicator, and that's a single point of failure. Right? That if there's a vulnerability in the input replicator, that can be exploited directly. It's not going to the two variants yet. But maybe the input replicator is simple enough we can implement it in hardware and have a lot of confidence that it's correct. We also have to have some way of dealing with shared state. Right, if we're sending the same request to these two variants and they're both sharing a database, well, they can't both send the same update to the database. So we either need some way of replicating the state as well, which gets pretty expensive, or we need some way of dealing with shared state. The other questions this poses, how do we actually get the security properties we want? We'd like some way of proving that we have two variants that are disjoint against some class of attack. This is more complicated than it sounds. One of the things we have to think about is multi-stage attacks. You could have a sequence of requests where no request by itself crashes one of the variants, but they get them in different states. And then a request that actually executes an attack successfully on one of the variants without crashing the other one. With the simple property that I described of splitting the instruction set, that's probably not feasible. With some of the other ideas like changing memory, that probably is. So we have to be very careful about the assumptions when we try to prove that the variants are really disjoint. The other thing we have to think about is, can we get higher level properties? Right? So all the examples I've talked about so far have assumed that the attacker needs to know addresses in the code or needs to inject instructions that run directly on the processor. And we seem to have pretty good ways of dealing with that. But lots of attacks don't rely on that assumption, that they can attack an application based on the higher level semantics of the application. And so we need to try to think of ways of making that kind of property disjoint. And so that brings me to the real jaws of the talk, which is when we try to understand how much security diversity is giving us, we have to think about the perspective of the attacker. So from the perspective of a parasite, all humans are very different. Right? From an influenza virus perspective, the diversity in human immune systems is good enough that one virus can attack all humans. From the perspective of a great white shark, well, humans are all really similar. They're all slow, they're all bad swimmers, and they're all really tasty. So if we want to get diversity that works against attacks that are more like the great white shark than the parasite, we need to think of ways of getting diversity in the way we run processes that is at a higher level than just at the instruction set or the memory addressing. So to summarize, diversity defenses have a lot of promise. They easily defeat all existing attacks that aren't designed to get around them. But a determined adversary may be able to get around them. And certainly, we've seen the examples today where ISR only protects the server for about 6 minutes against a determined adversary if certain conditions are true. But I think there is good promise here of doing things in security where we can actually prove properties. And the problem of protecting a secret won't be part of what we need to get security. So these are the students who did the work. Nora is a first-year grad student who did all the work on breaking the randomization keys. And Nate is about an N-2-year grad student who did the micro VM code. So any questions?
I would say the ISR will be, can avoid lots of code injection attacks, but may not be effective to the return to libc attacks. So just
right. So the return to libc attack doesn't require the attacker to inject their own code. It's using code that's already there, so it's already encrypted in the right way. If you can accomplish your goals with a return to libc attack, ISR won't help. Yes.
So this new architecture with the replicated servers, I mean, is it doubling the effort needed on the part? I mean, so it's preventing certain kinds of attacks.
Mm-hmm.
But more generally, is it doubling the effort that's needed, or is it making it, at best, doubling?
It could be more than doubling the effort, right? It depends on how you implement it. But at least the most secure way of implementing it would be to have completely separate boxes that implement the two variants. So there's no threat of them not being isolated. And that may sound expensive. Right? Buying twice as many machines, using twice as much power, certainly is expensive. I think if we go back to the analogy of what biology does to ensure diversity, it's probably a lot less expensive than what biology does. It may be expensive compared to other proposed ways of getting computers to be more secure. But it has a property that I think is desirable enough that maybe that cost is worthwhile. The other possibility is that maybe you can implement it on one machine, having separate processes, so the costs are not that high. We'd have to be a lot more careful to make sure that they're isolated enough. And so we're giving up a lot of processing power. We're running effectively twice as much. But processing power is effectively free now, so maybe that doesn't matter.
But let's say we are able to achieve this, let me call it complete isolation.
Mm-hmm.
Okay. Then what is the claim? Is it doubling the effort, or is it making it